For part 2 for this week, I'm going to cover the NIOSH lifting equation. I'll abbreviate it NLE, NIOSH lifting equation, and I'll assume you have a basic background in using the NIOSH lifting equation that you would have covered in an undergraduate ergonomics, undergraduate human factors type of class, at least a basic foundation to build on. The NLE is used to evaluate lifts and lowers only, and so you can't look at pushing, pulling, carrying, throwing, those types of activities. It's lifting and lowering only. The NIOSH lifting equation integrates biomechanical factors. It does give you recommended loads that are based on the compressional force being under 770 pounds. It does consider psychophysical factors. It's designed so that it is acceptable to more than 75% of females, or at least 75% of females. And it also, I haven't discussed this, but also considers physiological factors in which a person, it's designed so that a person doesn't become overly fatigued from extended duration or highly repetitive types of lifting or lowering tasks. And so out of these 3 different methods, it's going to limit by the most conservative, and it's going to be giving you, in some cases, it seems like a very conservative value. Again, and this offers the best protection for your workers. It recommends what a load should weigh if it's located in a specific position and lifted at a specific frequency, so that at least 90% of the potential workforce can lift with a low risk of injury. And so if you can get your loads down to your manual handling loading down to the NIOSH lifting equation recommendations, then you'll protect the majority of your workforce. They'll have a low risk of back injury. And it is focused on back injuries, preventing back injuries. The 90% is overall. It's designed so at least 75% of your workers are capable of lifting, and it's 75% of females and 99% of males. Okay, so it's the typical people that can lift safely. So overall 90%. The NIOSH lifting equation, it predicts a recommended weight limit, or RWL, and so this will be the output of the equation, recommended weight limit. The equation is posted on the slide. It's RWL is equal to a load constant times a set of 6 multipliers, and so the M's are multipliers. It's going to start out with a load constant of 51 pounds, and then these multipliers will either maintain that 51 pounds if it's a good condition, or will reduce the 51 pounds down to a lower value. And so the multipliers run from a value of 0 up to a maximum of 1. 1 keeps the load constant stable. Lower values closer to 0 will reduce the load constant. Okay, so recommended weight limit. The NIOSH lifting equation also has an added step. It has a lifting index, where an index is just a unitless number that's a ratio of the actual load weight divided by the recommendation. So Li is equal to the actual load weight divided by RWL. And then finally, once you determine the lifting index and interpret it, if you need to redesign, you need to apply controls, the multipliers, those HM, VM, DM, and so on up in the RWL equation, those will help tell you what's wrong with the lifting task, what you would want to control, what you would want to improve. The assumptions for the use of this equation, it is limited to 2-handed lifts that are performed while standing, and so you can't use this particular lifting equation if you're lifting while seated or you're lifting while kneeling. You have to be standing and has to use 2 hands. It's based on recommendations for working less than or equal to 8 hours. And so if you have 10 or 12-hour shifts, the NIOSH lifting equation really can't be used for those extended shifts. And then you can read through some of the other assumptions. The last one, your other material handling activities of pushing, pulling, carrying, shoveling, wheelbarrow use cannot use the NIOSH lifting equation. For the NIOSH lifting equation, you're going to be measuring a set of variables, and these are related to the multipliers. Measure a set of variables at the origin and at the destination, where the origin is the start of the lift, and the destination obviously is the end of the lift. And so over a lifting task, you'll look at a single lift, measure the start of the lift, and for example, if this were the start of the lift, this would be the origin, and say he's going to put it on a shelf right here. This would be the destination. So we have an origin where the load starts, and we have a destination where it ends up. At both of these locations, you're going to want to measure H horizontal, V, D, A, F, and C. H, the horizontal, is the distance between and it's a horizontal distance between the hands and the ankles. So it's a distance between hands and ankles. Okay, so that's simplified. It's midway between the ankles, so if your feet are staggered, it's midway between the two ankle bones and the middle knuckle on the hand. And so on my drawing, it is here. If I had the person putting the load down at the destination, it would be my distance from here to his, again, middle knuckle here. Okay, so that's measured with a tape measure. Vertical location is the distance of hands above floor. Distance of hands above floor. So at the origin, it is my middle knuckle is here, down to the floor. So we're always using the floor as a reference. At the destination, it is my hands down to the floor. D will be the travel distance. The travel distance. Similar to what the psychophysical Liberty Mutual tables use, it's just how far does the load travel, and it travels from the origin to the destination vertically by just the difference between the two V's. Asymmetric is the angle of twist in degrees, and it's just how much you're twisting your back. You're supposed to be facing forward. Do you twist fully to the side, 90 degrees? Do you twist halfway to the side, either right or left, 45 degrees? So it's the angle of twist. Frequency is going to be in lifts per minute. Lifts per minute. And coupling will be your grasp on the load, your grasp or your grip, and we're going to be evaluating it as being good, fair, or poor. Good, fair, or poor. Where good is, you have good handles, such as it looks like he has good handles on this box, or you can wrap your fingers around it. Fair is if this box did not have handles, he could wrap his fingers 90 degrees around an edge. So that's fair. And I use that often, so 90 degrees around edge. And poor is something that it's awkward, like a sack or a bag. You really can't get a grip on it very well, and so it's a poor grip. Okay, so after defining those, the next step in the undergraduate class, or many undergraduate classes, is to take those values you measure. For example, your horizontal distance. Maybe this distance here between his ankles to his hands, maybe that's 12 inches. Knowing that H is 12 inches, in your multiplier tables, you would go and find that H is 12. Right beside it is your multiplier, 0.83, and so your HM is equal to 0.83. So HM is equal to 0.83. Okay, so this was the undergrad. To ramp this up a bit for the graduate class, where instead of using those multiplier tables, we're going to use the equation method. And I cover this in the grad class. I want to make sure that you see this because I understand this might appear on the CSP exam. I ran into a former student a couple years ago, and they had just taken the CSP, and they said they memorized these equations for the exam. They needed it for the exam, and so I'm not making you memorize it, but I do want you to be familiar with using them. And so instead of using the multiplier tables like the undergrad, we're going to be using equations. And so your HM will be equal to 10 over H. If you had 12 inches as your H, that would have been 10 over 12. Okay, so you'll get a decimal value. I don't really like the equations because, well, it's just adding in more math, more potential for error, but I do want you to be familiar with them. But I also don't like them because you have to make sure that you check that the multipliers are not out of range. For example, if h is less than or equal to 10, and I had a former student call me, he was moving, his workers were moving bumpers, automobile bumpers, 2 inches. They were lifting them 2 inches. And he wanted to use the OSH lifting equation. I said, well, 2 inches really isn't accounted for. You would have to go a minimum of 10. Okay, so the lowest you can go is 10 inches. And that would make HM equal to 1. Back on the multiplier, you can see that these tables do it for you automatically. For h less than or equal to 10, it gives you an HM is equal to 1.0. Okay, but it's something that you'll have to double check if you use the equations. Similarly, on the high side, if h is greater than 25, you have to automatically set your HM equal to 0. Okay. If you ran the calculation 10 divided by 26, you would get a decimal value, but you have to double check this constraint that h is greater than 25, HM will be equal to 0. And the reason for this is if we're looking at reaches, so distance between your ankles to your middle knuckle, your arms are only so long. So a small female arm cannot reach more than 25 inches, and so if they can't reach, they can't do the task, they can't lift any weight, and so the recommendation becomes 0 pounds at reaches that are too far. For the vertical multiplier, again an equation, 1 minus 0.0075 times the absolute value. The thing to note here is absolute value. Go back to your math class. Absolute value means whatever you calculate within that absolute value, that is going to be positive. And so if you moved it if you were starting near the floor, if your knuckles were touching the floor, if you stuck your fingers under a box to lift them, so v is equal to 0. 0 minus 30, 0 minus 30 is a minus 30, a negative 30, but with the absolute value sign that makes it a positive. And so you have 1 minus 0.0075 times 30. Okay, so don't forget the absolute values, you must use those. And then the constraint on this, if V is greater than 70, small females can't reach higher than 70 inches, and so VM becomes 0 at high vertical locations. For distance, pretty clear cut, but again, check your constraints. They can't move more than 70 inches or less than 10 inches. Asymmetric is 1 minus 0.0332 times A, where A is the angle in degrees, and so if you were twisting 90 degrees, it'd be 1 minus 0.0032 times 90. FM, you will need a table. There's not an equation for this. Likewise, coupling, you'll need a table. There's not an equation for that. Okay. For frequency multiplier, the table is table 5. For example, if you were lifting at 2 lifts per minute, that's once every 30 seconds, 2 lifts per minute, you could have a frequency multiplier 0.91, 0.84, 0.65, depending on the duration of the task. For short tasks, the multiplier is higher. And then for each hour you put on the job, or I should say each category that adds hours of duration, the multiplier will be reduced. So 1 to 2 hours, it goes down to 0.84. 2 to 8 hours goes down to 0.65. Okay. The other thing to note is you have V's on here. V that's vertical is the origin. All of these V's are the origin V. So V at the origin. The coupling multiplier table, again, you have good, fair, poor as your possibility, good, fair, poor. This V is the hand position at the origin or destination, whichever one you're evaluating. Okay, so the V is whichever one you're evaluating. So you'd pick, for example, if you had a box, no handles, fair. If you were lifting below your knuckles, it'd be 0.95. If you're lifting above your knuckles, be 1.0. Okay. So working through an example is the best way to learn this method. An overhead trolley conveyor brings empty 17-pound totes to the operator. So he's standing there facing the totes. He takes the tote off of the J-hook while he's directly facing it. Then he twists 45 degrees to the left. So whenever the tote gets near the platform, as he's lowering it down, when it gets near the platform, he twists 45 degrees to the left, and without significant control, he drops the tote down a chute. So he's using gravity, and this chute is cut into the platform. And so essentially, he takes the tote off the J-hook, twists 45 degrees, and drops it down a hole in the platform. 450 totes are lowered in a 2.5-hour task time. And as you can see, the edge of the tote is 90 degrees. It has about a 90-degree edge. He can flex his fingers about 90 degrees around it, and so that we're told the coupling is fair. Okay, so given that information, we want to calculate the RWL using the NIOSH lifting equation. Something to note is we have an origin. We have an origin where he's picking up the tote. So this will be the origin. He's lifting the tote. The destination will be where he's dropping it down the platform, a chute in the platform. And so this is actually a lower rather than a lift. It goes from a high height to a lower height, or a high vertical location to a lower vertical location. At the origin, he will be reaching 23 degrees from his ankles out to his middle knuckle. And that would be inches, not degrees. Sorry about that. So 23 inches. And he's reaching to a vertical location. This will be the maximum allowable, 70 inches. Any higher, he wouldn't be able to reach it. Okay, but that is V. When he puts it down at the destination, this 10 is meant to show you the H of the destination. And when he puts it at the destination, the V of the destination is 30, and he's twisting 45 degrees to do that. Okay, so given that setup, we're going to look at the origin first. We always calculate the origin. We want to know essentially how risky is the origin. And so using those equations, I've just rewritten them on this slide, we want to find RWL by calculating the HM, VM, DM, AM, FM, and finding FM and CM. Our load constant is 51 pounds. We always start, if we're using the US customary, is 51 pounds, or if you're a metric, 23 kilograms, but 51 pounds. Our HM is 10 divided by H. H in this case, again, we were reaching 23 inches in front of the body. So 23 inches between the midpoint of his ankles out to his middle knuckle. And so that's 10 divided by 23. We could go back and check that 23 fits within, it's greater than 10, it's less than 25, and so we can use the equation to calculate that. Plug that in our calculator and we will get that our HM is equal to 0.43. Our VM is 1 minus 0.0075 times V is 70 minus 30 is equal to 0.70. DM is 0.82 plus 1.8 divided by D, where D is 70 minus 30. So this D is 70 minus 30. Okay, so he's moved at 40 inches. DM is equal to 0.86. AM is equal to 1 minus 0.0032 times our angle of asymmetry. Whenever he's reaching for the toad, he's directly facing it. The twist in his back is 0 degrees. And so AM is equal to 1. FM FN, we have to use the frequency table. We have to first find out what is the frequency. So frequency in lifts per minute. Frequency was 450 totes were lowered, so 450 lowers, divided by the task time was 2.5 hours. We need lowers per minute. Lowers per minute, so we have to convert 2.5 hours into 60 minutes per hour. And that'll equal 3 lifts per minute. I'll abbreviate it LPM, lifts per minute. So we know we're at 3. Second consideration is the work duration. Is it, we see it's 2.5 hours long, 2.5 hours. It doesn't fit in the 1 to 2. It fits in the 2 to 8, so we're over here. And lastly, we know it's 0.55, but our V at the origin is 70. 70 is greater than 30, so 70 is greater than 30, and so we're at this 0.55. So FM is equal to 0.55. And then lastly, coupling was fair. Flex fingers 90 degrees around the edges was fair. Our V was 70. 70 is greater than 30. And so we're at 1.0. So CM is equal to 1.0. And so our last step, once we have all these intermediate calculations, the last step is just do that final multiplication. 51 times 0.43 times 0.70 times 0.86 times 1 times 0.55 times 1 is equal to, don't forget the 71 by the way, or sorry, the 51. Don't forget the 51 over here. Plug those in your calculators, you're going to come up with a 7.26 pounds as our RWL. Okay, so origin done. Destination. Destination we do only if there's significant control, where significant control means that you're careful with the load when you put it down. Was he careful with the load when he put it down? It's like, no, he dropped it. Oops. No, he dropped it. It was done without significant control. Okay. If a lift is done without significant control, that means his body's not affected. He's not controlling it significantly. And so you ignore the destination if there's no significant control. So ignore the destination if there's no significant control. If there's no significant control, his body's not at risk, you ignore the destination. Okay, so final step is we want to go in and calculate the lifting index and interpret it. So lifting index is equal to the load weight divided by the RWL. In our case, our load weight, how much did the totes weigh? They weighed 17 pounds was the actual weight. Our RWL was 7.26 pounds. Pound will cancel pounds. Our lifting index is 2.34. 2.34. Okay, again, unitless, pound divided by pound. The interpretation on this, NIOSH interpretation, if the lifting index is less than or equal to 1, you want it to be small, there's little risk, the lift is considered safe for at least 75% of workers. At least 75% is the 75% of females, but overall typically 90% of workers if you consider males and females. So this is NIOSH, and NIOSH says if it's not less than or equal to 1, if it is greater than 1.0, redesign. Some people are at risk. Some are at risk. So redesign, some are at risk. Okay, so that's the official thing, is if it's low, less than or equal to 1, we're good. You're done. If it's greater than 1, redesign according to NIOSH because some workers are at risk. In real life, ergonomists have said, well, that's too conservative. We don't typically find problems, injuries when the lifting index is between 1 and 2. It's probably okay without redesign, so that's an unofficial interpretation. But whenever you get to the 2 to 3 level, risk is present. You want to redesign it. And then if the lifting index is greater than 3, there is significant risk to most workers, even your strongest, most fit workers. You must control it. And so unofficially, well, I should say officially, NIOSH would say this is greater than 1 redesign. Okay, so that's NIOSH. Ergonomists, practicing ergonomists say it does fall within 2 to 3, so yeah, redesign that. Redesign, how do you redesign it? You go back to your multipliers. You've got multipliers HM, VM, DM, and so on. You go back for your smallest multiplier, numerically smallest, you give that a number 1. So out of all our numbers, our smallest number here is 0.43. We'll give that a number 1. And we'll just keep ranking these. Number 1, 0.55 gets a number 2, 0.70 gets a number 3, 0.86 gets a number 4. 1 can't do anything with, and so we would redesign this. Okay, so this is the worst thing about the job, this HM. HM is reaching 23 degrees, and so our control by decreasing H to, for example, if we could get it down to 12 inches or 15 inches, that would help improve the task. And then in real life, you look at how could we get that down to 12 or 14 or 15, or just reduce it down from 23. And you could say, well, we could cut off the platform. We could move the J-hook we could move the J-hook conveyor. We could bring it out closer to the worker. And so you just start looking at what are alternative ways to accomplish that, to reduce H so that we have a better HM.